Good morning, this is your Stat Sensei, Mr. Spensei, and this is an assignment. This will be a hypothesis test on one sample proportions, and our scenario is checkout thieves. So, a manager at a grocery store is concerned about theft at the self-checkout lane. So, we care about the self-checkout lanes, probably need to underline that, make a point of it. The store has cameras installed to monitor activity and noticed an increase in theft. So, increase, that's probably going to be important. That's probably going to speak to what our alternative is. The manager selected a random sample. Okay, random sample, that's our first condition of 250 transactions. So we know our sample size is 250 at the self-checkout lane and found that 18 of those involve theft. And this is what we care about. So that sounds like 18 will be our X value, the number of successes, in this case, the number of thefts. The store handles over 5,000 self-checkout transactions. So it sounds like we have a population of about 5,000, and that's going to be important for conditions. It says at the 3% level. So we know at this point, oh, we have an alpha equal to 0.03. Is there evidence that more than 5%? So we're making a comparison to 5%, and we have the word more. More tells me we're looking for a greater than. So our alternative looks like it's going to be P is greater than 5%. All right, which means we have a population P or the comparison P of 5%, and that'll be our null hypothesis. Well, we've already stated that we're going to be running a hypothesis test, and remember, it's the sample proportion minus the population proportion. Please make sure that you pay attention to this. When we're working with a hypothesis test, we are using the claim, we're using the PO or the population proportion. So please make sure that you note that when we're running a hypothesis test, we're using P for our standard deviation. When we're running a confidence interval, we're going to use P hat. All right. Well, we've got a lot of our information already from our reading. We said, okay, 18 thefts out of a sample size of 250. And we said our comparison or the claim is 5%. That's what we expect. But they did not give us p hat in our scenario, so we have to calculate that out. And to calculate that out, we take the 18 thefts divided by the 250 that were surveyed. And if we go 18 divided by 250, we end up getting 0.072. As we already know, this is going to be a one proportion z-test. So the one thing to keep in mind is when we're actually drawing this, we're going to be centered when we're working with a hypothesis test, we center on P. So when we're working with a hypothesis test, we center on P. If we're working with a confidence interval, we're centered on the sample proportion. So when we draw this out, we're going to be centered on our population proportion of 5%. And just remember that's 5 divided by 100, the 5% divided by 100%. And this is our sample proportion. Notice we shaded greater than. Why? They said more, so we know this is a greater than. And when we plug in, it's pretty simple. Plugging in the 0.072 that we calculated for the sample proportion, the 5% for the population proportion, and remember the 5% goes down here. All right, then we need to go ahead and write our hypothesis. Well, the claim is, or what we're comparing to, is the 5%. So our null hypothesis, as always, is an equal. Please make sure this is always equal. So equals 5%, or if you'd like, 5 divided by 100 gives us 0.05. So you could have said HO, where P equals 0.05. All right, an alternative hypothesis would be HA P is greater than 0.05. Please remember that 5% or this greater than is consistent with the greater than. The greater than here is consistent with it here, is consistent with the word more. So that all needs to be the same and related. So please make sure you have that going. So when we look at this, we also need to know that we need to define our parameter. What is it we're interested in? Well, we're interested in the true population proportion. And remember, we're using the word proportion now because we're not working with means any longer. It's the true population proportion of thefts in the self-checkout lane. And remember, we said earlier we cared about the checkout lane. That's what we're concerned about, is where those thefts were occurring was in the checkout lane. So our conditions, well, the first condition is, well, do we have a random sample? And if we go back and we look back, it says, oh, they took a random sample of 250 and we had a population of 5,000. We're going to need both of that, all that information. So our first one is the random sample. Is it random? Yeah, it was random sample of 250. They told us that. It was given. That was great. Piece of cake. The next one, we need to make sure that our sample is not too big. And so we're going to take our sample size of 250 and multiply by 10. And we get, and this should have been a 250. Multiply by 10 and we get 2,500. Well, our population size that they gave us was 5,000. 2,500 is less than 5,000. So N is less than 10% of the population. That condition is checked off. So that was making sure it wasn't too big. Now we need to make sure it's big enough. So we're going to have to go, and please remember, this is super important. If we're working with a hypothesis test, if we're working with a test, we need to use P. If we're working with a confidence interval, we'll use P hat. So our sample size times 0.05, that equals 12.5, and that's greater than 10. So this is good. All right. 250 times 1 minus 0.07, 0.05. You know what? I need to check that out. That may have some wrong numbers there. 250 times 0.05 is 12.5. That's good. This should not be 0.072. This should say 0.05. So this would be parenthesis 250, 1 minus the 0.05. And we end up getting 237.5. And that's also greater than 10. So the sample is large enough. All right. So that one checks out. So that takes care of all of our conditions. The first one, random sample, they told us that. Then we go, all right, 250 times 10, and the sample size of 250, it wasn't 300, times 10 is 2,500 and gives us 5,000. And then we take the sample size times the population proportion. So if 250 times 0.05, we get 12.5. That was greater than 10. Not much greater, but it is bigger. And then we have the sample size times 1 minus the population. So 250 times 1 minus 0.05, and that equals 237.5, and that's also greater than 10. So we've done all that. So the next thing we need to do is actually run the test. So let's go into and do that. Stat test, one proportion z-test. Our population proportion was 0.05. They gave that to us up um, up here. And then our X value is 18, which is right here, 250. We said greater than, and notice that's what we had here. And that's what we also have as our alternative hypothesis. So that's consistent. And we end up getting a z-score of 1.596 and a p-value of 0.055. So z is greater than 1.596, and that equals 0.0552. This should have said 0.03. All right. Well, 552 is definitely bigger than 300, so we're going to fail to reject. So our p-value is 0.0552, which is greater than our alpha of 0.03. We fail to reject. This first part that we just wrote comes straight out of this box right here. P-value of 0.0552 is greater than our alpha of 0.03. We fail to reject. It's exactly what we have right here. And then there is not Super important that this is a not, if it's a fail, there's not sufficient evidence to suggest that the true population proportion of thefts in the self-checkout lane is more than 5%. So let's break that down. True population proportion of thefts in the self-checkout lanes. Oh, the true population proportion of thefts in the self-checkout lane. Hey, that was our parameter. So that's just a restatement of our parameter. That's there. Then the more than 5%. This right here is always a restatement, always, every single time, a restatement of our alternative. So this is a restatement of HA. Okay, well, that concludes this video. I sure hope it helps and I sure hope you excuse a couple of those mistakes. Appreciate you. Thank you.